Okay, you are in talk 2 of session 1 of part 1 of fifth day of the conference. And the next speaker is Gyo Taek Jin from KAIST in Korea. And he's going to talk on arc index and minimal grid diagrams of the prime nodes with 14 crossings.
Thank you,
So
Sophia. Thank you for the introduction. I'd like to thank the organizers for inviting me to give a talk in this wonderful conference on the occasion of Kaufman's 80th birthday. So, the finding minimal grid diagrams of 14 crossing knots started from the year 2005, and we published it, an article about arc index 10 case, and it includes 17 prime knots of 14 crossings. And this article appears in the 40th volume of NAS and Everything. And later in 2011, with Wangun Park, I found also 477 prime knots of crossings, 14 crossings with 11 arc index 11. And then in 2021, we published it, article on 14 crossing, 12 arc index 12 prime knots, and it includes 3,180 prime knots of 14 crossings. This article appears in the Journal of Korean Math Society, but it only includes the 10 crossing knots, and the list of 14 crossing knots appear in the corresponding article in the archive. And for the 13 crossing, arc index 13 case, we found 8,027 14 crossing knots, and this article is in the archive, and it's submitted last year. And then for the 14 crossing case, arc index 14 case, we finished last year, and then the article is still in preparation. And there are no arc index 15 knots for the 14 crossing knots, and you will see why. I'll explain later. And then the arc index 16 case is the alternating knots. So and the number of alternating knots of 14 crossings is 19,536. And then we also are preparing an article on this. So the last two items were finished last year. And those names with a star, so they are, at the time of the research, they are high school students. The high school is for gifted students named Korea Science Academy of KAIST. Okay, so a grid diagram is a knot diagram which is composed of finitely many horizontal line segments and the same number of vertical segments, such that line segments always cross over horizontal line segments, as you see in the figure. And for any knot diagram, you can deform it so that it has only horizontal segments and vertical segments. And then if there is a horizontal segment going over a vertical segment, then you make some twist, like in the figure on the right. So that shows every knot admits a grid diagram. And a knot in space is said to be in an arc presentation if it lies in the union of finitely many half planes with a common boundary line such that each half plane contains only one simple arc of the knot. And the figure on the bottom show figure 8 knot in 6 pages, embedded in 6-page open book. The arc index arc presentation was first considered by Brun in 1897, and Cromel brought it to our attention in 1995. And yeah, so every knot admits an arc presentation. So every knot admits a grid diagram, as I told you just before. And then you can bend horizontal segments so that it touches a vertical line vertical axis behind the diagram. Then as you see, the vertical segments correspond to a plane containing an arc in the half plane that has common boundary line along the axis. And the minimum number of half planes among all arc presentations is called arc index, denoted by alpha of k. And the smallest size grid diagram is minimal, and the minimal grid diagram has vertical segments as many as the arc index. Same for the horizontal segment. There are various ways to describe the arc presentation. So here's a wheel diagram. It's a projection of the arc presentation into the plane, perpendicular to the plane, the pages, perpendicular to the axis, and then so it's a graph with one vertex and many edges, and each edge has a pair of numbers indicating the two ends of the arc, the relative height of the endpoints of each arc in all the pages. And the grid diagram I explained just before. And for a grid diagram, we may not draw the horizontal segments broken by understanding that the horizontal line is below the vertical line. And Kronemann matrix is a square matrix of zeros and ones, such that every row and column has exactly 2 ones. Then by joining the ones with horizontal segments and vertical segments, then you get a grid diagram. And we can also describe it arc presentation by a sequence of pairs of numbers like this: 2, 5, 4, 6, 1, 5, 3, 6, 2, 4, 1, 3. So that is can be obtained from the wheel diagram, reading these pair of numbers starting from 2.5 counterclockwise. You can read from anywhere and then in any direction. Yeah, and then so in the Kronemann matrix, just suppose the lower bottom entry is at 1, 1 of XY plane. And then the first column, these numbers appear at 2 and 5 in the Y coordinate. So you can read this sequence of parallel numbers from the Kronecker matrix and vice versa. So here's a theorem proved by Iron Knott in 1997. So the arc index of K is bigger than or equal to 2 plus the breadth A of the modulo 2 Kaufman polynomial. And so the breadth A means the highest degree minus the lowest degree. And in the following year, Hugh Morton and Elisabetta Beltrami improved this so that the arc index is bigger than or equal to 2 plus the breadth A of the Kaufman two-variable polynomial. And it turns out when we have a alternating knot or link, then this breadth A is to the crossing number. So for alternating knots, arc index is lower bound by crossing number plus 2. And in 2000, Yongju Bae and Chanyoung Park proved that if K is non-split, then arc index is not bigger than crossing number plus 2. And in 2010, with Wangun Park, I proved if K is non-alternating and prime, then arc index is not bigger than crossing number. So that's why there are no arc index 15 knots for crossing number 14. And combining these theorems together, so we have this corollary. So K is a prime and alternating, then arc index is exactly crossing number plus 2. And if K is prime and non-alternating, then it's lower bound by 2 plus breadth A of Kaufman polynomial, and upper bound by crossing number. So not listed knots and links up to arc index 9, and this table shows only the prime knots, and his list contains composite knots and also some links. And for index 10, 11, and 12, with many others, I found the minimal grid diagrams and arc index of these many prime knots. And for the case of arc index 13, 14, 15, and 16, so we used the different method, filter spanning tree method, which I will explain later. And for prime knots of crossing number 3 up to 13, the minimal grid diagram appear not in full, so you can get the grid diagram and also the minimal the arc index, and so those with red numbers are published in archive, and those numbers in green, we are still preparing articles. Okay, so we started from dark tetracycline code, in DT code in short. So here we have this 819, which is the torus number of type 3-4, and anywhere from starting from anywhere in the diagram. So we start assigning numbers to every crossing. So you go in any direction until you go and come back to the original position. So you assign numbers 1, 2, 3, and up to 2n when n is the crossing number. So and every crossing has two numbers, one even and the other odd. And at an overcrossing with an even number assigned, we make the even number negative. And then the sequence of even numbers corresponding to the increasing odd sequence is called a Dow-Tetracycline code of the diagram. So for this diagram, so the DT code is 6 minus 10, 16 minus 12, minus 14, minus 4, minus 8, and 2. So here, so for 1, it's 6. For 3, it's minus 10 because 3 goes under, so the 10 goes over. So it becomes minus 10, and so on. And a DT code or knot diagram determines the knot type up to mirror images. The main source of our source of the DT code is the Knotscape program. So you can get Knotscape from Thistlethwaite homepage, or maybe Jim Hastie homepage. For the arc index 10, 11, and 12, we used the chromium matrices. So for a chromium matrix, the norm is the binary number obtained by juxtaposition of its rows. And for each of 10, 11, and 12, we generated all n by n chromium matrices in the following in the norm decreasing order, and we eliminate those having consecutive ones horizontally or vertically, because then you can easily reduce the size, and whether it corresponds to a link or if it is visually composite, then we throw away. And when you have interchangeable consecutive rows and columns, resulting a norm increase. So this is the change correspond to either planar isotopy or random isotopy 2 move. So and then if such change ever increase the norm, then the knot equivalent, so it must have been handled previously, because we are generating the matrix in the norm decreasing order. And also, if reflection or rotation of the matrix ever increase, then we throw this away, because it must have been handled previously. And then we use NotPlot program to obtain the DT code of the grid diagram corresponding to the remaining matrices. And then we test the DT code using a NAScape to identify whether that is has the crossing number crossing 10 or 11 or 12. So that's for the arc index 10, 11, and 12. Then for arc index bigger than 12, we needed this method, not spoken diagram method. This is the method Bae and Park proved their inequality. So this method deforms a C-crossing knot diagram into a single multi-crossing diagram with C+1 leaves. Here's an example. So here you have a figure 8 knot, and then we start from any from this crossing which is as marked, and we give height 5 for the overcrossing strand and 4 for the undercrossing strand. And then we move this undercrossing arc over here. And then because the moved arc is a low underpass, so we assign one smaller height, and then we drag this on the crossing arc over here, and then we assign 2 at these 2 ends, and then we move this over here, and that is an overcrossing, so we give height 6 to these. And then, so this big loop has both end height decided, and then we assign in the middle, we assign height 1, and then bring it over here, passing these 2. And then we have this 6 loops, all so without anything nested. And then these 2, so you can bend it so that it becomes vertical with respect to this plane, and then you get this wheel diagram. So at each step, you assign a new height to both sides of the moved strand. And then at the end, the unique non-innermost loop will be replaced by 2 loops. So this method was used to prove arc index is less than or equal to crossing number plus 2. So we modified this method so that it can be programmed in computer. It was joint work with Hwa-jung Lee, by former student. And this method constructs a sequence of edges forming a spanning tree on a diagram, and assuming each edge of the tree has a constant height, and assign a new height to the strand at the new end of the edge. So we start from the same figure. Then instead of dragging on the crossing, so we just stretch an edge, and then assign the height 3 at both sides of the on the crossing, and then we stretch another edge, and then assign 2 and 2, And then you stretch the last edge and assign 6 and 6 because this is an overcrossing. So, and then we assign 1 and then so we make this wheel diagram, and we will show you. I'll show you in more detail for 14 crossing knot in a minute. So the remaining edges will form a wheel diagram of C+2 spokes. So these sticks will be called spokes. Okay, so here's the case of arc index 13. So so the method the both method will give 16 arcs, but we have to reduce it by 3. So here this knot is 14 and 10. So and obtained from a snap pi. Okay, every non-alternating prime diagram of a knot has at least 4 non-alternating edges, which are located in the boundaries of at least 4 regions. And at least 2 of the non-alternating edges, and about half of them, in most cases, can be used to reduce the arc presentation. So that's proved in an article with Park, Wangdon Park. So this diagram of 14 and 10. So the non-alternating edges are marked by circles and dots, and so they belong to boundaries of 6 regions, including the unbounded region. And in the following, we show how these 3 non-alternating edges marked by dots are used to reduce the arc presentation by 3. So okay, there are at the time we started this, there are 23,762 prime knots of crossing 14 crossing, which have arc index either 13 or 14. And then we found 6,295 knots having 6, 8, or 10 non-alternate edges in their diagrams. So diagrams mean from the DT codes from Netscape. And then so this 14 and 10 in Netscape has the DT code 4, 8, 10, minus 4, 2, minus 16, and so on. And among the 6,295 knots with more than 6, more than or equal to 6 northern edges, we've generated 50 spanning trees of 3,353 cases. So for this 14 and 10, we have this tree. So the edges numbered together is a tree, and it's a spanning tree. And the numbers mean the order the edges are added. A filter spanning tree on a prime knot diagram is a sequence of edges forming a maximal tree with the following conditions. So each partial sequence is connected. So it's a tree. At every step, it's a tree. And each partial sequence must not separate untouched crossings into 2 parts. And except that the last step, avoid choosing an edge whose one-step extension in the same direction makes a loop. So for example, after edge 11 is added, do you see my my mouse? And then if you go further, this vertex is free of other edges. But in the last step, you cannot avoid having you cannot avoid the extension to meet another vertex, because it's already a maximal tree when you choose 13th edge. So and then so this edge will play. We have to divide this into two parts later. I'll explain more. Okay. So here we take a tubular neighborhood of the spanning tree. So this black curve is actually a circle. So among the 28 edges of this 14 crossing knot, 13 are used to make the tree. So these 13 are inside the tubular neighborhood, and the rest 15 are outside the tubular neighborhood. And we deform the diagram so that the tubular neighborhood becomes round, as in the figure on the right. And each of the outside edges contribute one page in the resulting arc presentation, except the one extended from 13th edge. So this 13th edge extension is this one, and it corresponds to this curve where I marked this plus sign. So we're gonna break this into. I mean, we're gonna bend this, and then we give some extra height here, as we did with the figure A knot. So we construct a wheel diagram for this 14 and 10 using a tree. So this the root is marked here, and then we assign height 7 and 6 for this undercrossing underpass. Overpass we give 7, and for underpass we give 6. And inside this tubular neighborhood, the strand from one end of from one of the boundary point to the other boundary point, the height is constant height. It has constant height. So here's the first edge, and then we meet a strand which goes over, so we give a height 8. And then for the second one, we also meet an overcrossing, so we give a height 9. And then this arc outside the tubular neighborhood has both ends at 8 and 9. So we get a spoke of with the boundary information 8 and 9. And then we keep going like this. So and then and here we have to because the one enclosing another arc, we need to decide whether we should put a spoke here or here. But the interval 11, 12 and interval 3, 4 are not interleaved. So you can put the spoke anywhere in these two ends for this arc. Wait a minute. But for this one, this has level 13 and 6, and it includes another arc with endpoints spanning 3 and 12. And this number 6 is between 3 and 12. So these two arcs are interleaved. So because 6 is here, you cannot put this over here. So you must put this over here, because 13 you can pass, because 13 is bigger than 3 and 12. You can pass this over here. So you must put so you need to decide where to put the spoke when the nested arcs are interleaved. And then when 13ths are added, the 13ths are added. Where's the 13th? So yeah, it's here. It's when 13ths are added, and then all arcs outside the stable neighborhood except this one gets assigned a spoke. But here for this one, so its endpoints are 6 and 1. Sorry, 6 and 9, and 9 is between 7 and 13, and 6 is between 1 and 14. So you cannot put anywhere spoke anywhere in this situation. So you are forced to add an extra height, which is one smaller than all the smallest, or one bigger than the highest height among all these. So we give 16, which is the one bigger than the highest height among all strands inside the stable neighborhood. So so that gives you 16 arcs. So now you have this spoke wheel diagram of 16 spokes, and then you read the spoke information from anywhere around this wheel. So it and then you can draw this grid diagram. So 114 is so it's a level 1 to 14, and then 7, 13, and so on. And notice that there are unit length vertical segments. So you can remove this by straightening. So so you can straighten it. Then in 3 places, you can reduce the size by 3. And then you can do some moves to make the diagram to have similar looking. I mean, so I prefer to have a narrow top on the left. So so you can for grid diagrams you can move vertical segments on either side to the other side, one by one, or you can put them together, or you can also reflect. Okay, And then so from this diagram, you read you make this into three-dimensional. So bend this horizontal segment to have smaller z coordinate in the middle, just like this diagram. So you find this coordinates, and then you read it from the knot plot, and the knot plot draws this diagram, and then you can ask for Dowco. So it gives this Dowco code, and you from the Dowco code. So it has 30 crossings. So it shows there are how many crossings there, and then in front of this Dowco code you add 30 and a dummy number, and then you ask Netscape to read it, and then it returns 14 and 10. So there have been some so there are 27,436 prime non-alternating diagrams with cross number 14. And among them, 17,477, 3,180 have architects 10, 11, and 12, respectively. And the remaining 23,762 have architects 13 or 14, as I said before. And among them, 15,735 knots have architects 14, as determined by the lower bound obtained from the Kaufman polynomial. So there are 8,027 knots to be determined, whether they are of 13, architect 13 or 14. And then, first attempt, we decided 3,353 of them are of architect 13. And then for the rest, we used this randomizer move 3. So the randomizer move 3 increases or decreases the number of non-alternating edges by 2. So we sorted out some those the alternating edges increase, such as 14 and 7951. So we decided 1,684 more as arcindex 13. And we still have 2,990 left, and then we changed the diagram without increasing the number of crossings, and then we repeated the same method, and then and still we had 523 left, and then for these we generated grid diagrams of size 13, and then we tested whether they are of one of these knots, and then we successfully found grid all the remaining ones as arcindex 13. So here you have this first 216 prime knots with arcindex 13 and crossing number 14. So here you have bigger diagrams. And for the case 14 and Archimedes 14 and 16. For the Archimedes 14 case, we need to find a grid diagram with unit length vertical segment in two places, and that's pretty easy because every non-alternating diagram has at least four non-alternate edges, so you can successfully find two places. And for the Archimedes 16 case, that's the you don't need to find anything. You don't need to reduce, and you cannot reduce by the theorems. And so you can compare these three nuts. So they have same projection, but as differ by so for this one you change these two crossings, that you get this, and then if you change these two crossings, you get this.
Is it only me that I have
This,
lost connection?
we've done yeah, I'll quickly finish in 2 minutes. And then for this one, for 14 and 20, we reduce by 2. So like this. And then you have this lower bound from Kaufman polynomial breadth A. So so these nuts have Archimedes 13, 14, and 16. And then you change the shapes. And then here you have first 216 for alpha equal to 14 and crossing over 14. So here you have bigger diagrams. And for the Archimedes 16 case, I show you first 162 because it's here. So happy birthday, Lou. And then here you have bigger diagrams. And the references. Thank you.
Wow, how impressive, especially the last slides. Thank you very much, Gyo Taek. That was a beautiful talk. Very interesting, amazing work. Let me stop recording.